from this point until pretty much the end of the day, we're not going to look at single terms x1 times x2, but we're going to look at problems that look like this. These problems have a bunch of terms that are products between variables and some terms that are actually squares of other variables. This is very easy to define. It's a quadratically constrained optimization, quadratically constrained quadratic problem. You have a quadratic function at the objective function, and you have a bunch of quadratic constraints. We saw yesterday that if Q is Q0 and all the Qk are positive semi-definite, then the problem is convex. It's really convex because there are no binary or integer variables in here. And there are very good solvers that can solve very quickly, very efficiently problems of a very large size, because the problem is convex in the case that all the Qs are positive semi-definite. If one single Q is positive semi-definite, things start to crack a little bit. There's nice conditions for which this, you can still solve a problem with a single non-convex quadratic efficiently, but in general, if you have multiple non-convex constraints, the problem becomes hard. What you saw yesterday with Sven is, in this case, then you treat all the constraints and you decompose their expressions. So I didn't write it there because it's a bit more compact like that, but all the all the quadratic constraints, all the quadratic forms are just sums over I from 1 to n of sums over j from 1 to n of qij times xi times xj. Plus something else, blah, 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 less or equal than c. It's not very important to us. If anything, what you should have understood yesterday is that this whole thing is a non-convex function that is actually a sum of non-convex functions themselves. And in principle, what we need to do is try to find the tightest possible convex relaxation of a set that is described by this non-convex function. Let me repeat it. It's a non-convex function that is, it doesn't always happen, that's the sum of multiple non-convex terms. This is very important. And the branch and bound for non-convex optimization would simply create a new auxiliary variable that we call yij from now on, and which we would like to impose a constraint yij equals xi times xj, so that we can simply substitute the yij in this quadratic form. That's no longer a quadratic form, it becomes a linear form. Obviously, the problem doesn't become convex all of a sudden because we still have these nasty non-convex constraints. The cool thing about that is that at least we decompose them. And if you think about it, this is the set that we just saw in the previous half an hour. So if we add McCormick inequalities, and if we derive some bounds on the yij, then we can add the other inequalities, the lifted tangent inequalities, then we still get only with those inequalities a lower bound. We get a relaxation. We get a convex relaxation. Because then we just replace this with those inequalities, and we have a linear inequality here. In general, a relaxation done only with these inequalities for the single terms xi and xj, such relaxations are horrible. They give you a very, very bad lower bound. So from this point on, we are going to look at problems at cases of quadratically constrained optimization, where you get better bounds by looking at the whole quadratic form, because since that's a function that includes a lot of quadratic terms, all using the same set of variables. So that needs to give you some edge, some advantage. So the first thing we'll do is write everything in matricial form. So if you create a new variable yij, you're gonna end up with a problem that looks like this. This is only a reformulation, like the one that you saw yesterday, where you simply introduce new variables. the Yij that are supposed to be equal to xi times xj. So we didn't do anything here. We went from a non-convex problem to a non-convex problem with a lot more variables. So we didn't do a big deal. Notation-wise, I'm, as I say here, Q, I don't know how you call it, this bullet, Y is simply the element-wise product of two matrices Q and capital Y. And you will also find it in the literature as the trace of Q times Y. So these Q and Y here are multiplied together with the matrix product. If you take the trace of it, because Q and Y are both symmetric, you don't need to transpose them, the trace of this product is exactly the same thing. You take the first row, first column of the first and second matrix, you multiply them together, you do the same with every element, and then you sum everything together. This is the bullet, this is the interior, let's call it the inner product between two matrices. Okay? So now we have a matrix Y that is, that in principle has n squared terms, but in fact, and in position ij, it will have a variable Yij that's the same as the one in position ji, simply because Yij is the product between xi and xj, Yji is the product between xj and xi. So you end up with a matrix that has an O of n square terms, but it's only half of the matrix that really gives you the new auxiliary variables. Let me rewrite it here. Let me stress again that I write it in red because those are the bad constraints. Big subject of research, they are non-convex, and people are trying to find all possible ways to approximate them for several cases. So this is the Y matrix, and X times X transpose is a product of a column vector times a row vector, which gives you exactly a matrix with the same size as this, and that's just a repetition of those single terms put into a matrix this time. Okay, there's a nice paper by Saxena, Bonamy, and Lee, Anurit Saxena, Pierre Bonamy, and John Lee, that does the following. Okay, so take this nasty constraint, Y equal, the matrix constraint, Y equals X times X transposed, and take any vector, any constant vector, so just choose one n-dimensional vector C at random. Okay, so I introduced it at C, but then I use D all over. So I'm sorry, that C over there is just a D. So D is your vector, n-dimensional vector that we'll use in the rest. So now take the same product, column vector times row vector of D, multiply it element-wise by Y. And if Y is supposed to be equal to X times X transpose, then by pre-multiplying both members of the equation by D times D transposed, what you get is this equation here. So these two, that's just pre-multiplying two members of the equation. But if you look closely, if you squint a bit, this thing can be rewritten as the square of an inner product between the two vectors D and X. You agree? So now you have a scalar quadratic constraint. A quadratic constraint is D transpose X squared equal to D transpose inner product Y. Is this constraint linear or nonlinear? Nonlinear. Is this part nonlinear? Is the right-hand side linear or nonlinear? It's linear because this is just a weighted sum of the variables in the matrix Y. This is instead a linear function squared. So this is again, it's a scalar quadratic function. What we could do here is, this is nothing really important. It's just a way to write the McCormick inequalities in matricial form. But what's important here is that first, if you just didn't look at this and just consider the McCormick inequalities, clearly by just looking at relaxations of the single product terms, you would get a set of X and capital Y satisfying only the McCormick inequalities. There's obviously going to be a relaxation of the original set, the original non-convex set with this nasty constraint. This constraint here by itself, simply because we took a matricial non-convex constraint and we just took an inner product with a matrix. This is also a non-convex constraint. This non-convex constraint is well, it's the intersection of two constraints. So D transpose X squared lesser than or equal to D transpose inner product Y, obviously, and D transpose X squared greater than or equal to D transpose inner product Y. Are these two constraints convex or non-convex? This is convex, right? Square of something less or equal than a linear term. It's like xy less or equal than x squared less or equal than y. This is non-convex. This is a bad non-convex constraint. Since the paper does it, we'll do it as well. This constraint, if you look at it, you take just the direction d transpose times x. So you take any vector d, it gives you a direction. Actually, it gives you a direction. And then you plot the function. This is d transpose x, and this is d transpose x squared. What you're going to get is you would like this to be, let's suppose it behaves like this, because it's a square greater or equal than a linear form. If it's something like this, then you would like to have a curve. You have a curve that's a quadratic curve that says d transpose x square equals d transpose inner product y. In principle, if you take the square is less or equal than this, then obviously you're going to get the part inside the parabola. So the nice constraint up there gives you an obviously convex set, the interior of the parabola, and the boundary plus the boundary of the parabola. The non-convex set instead gives you, and this is what is of interest to us, the part below the parabola. So this much more interesting set outside. And we suppose that d of x, d times d transpose x has lower bound and upper bound. So d transpose x lower bound is here, and d transpose x upper bound is here. What happens now? Well, we would like to satisfy both constraints. One is convex, and we can just plug it in. We put it in the solver, it will work. This is non-convex. We don't want to work with non-convex constraints because we're actually writing something that handles non-convex constraints. What could we do in here? You remember yesterday what happens in the branch and bound when you have a non-convex set, a non-convex constraint that is not satisfied at equality. There was a similar picture there. You branch, right? And you branch here, so you choose one point, which is d transpose x star. And based on that branch, you would like to have, if you had the secant at the beginning, to give you the convex solve. Now you have a branching point here, which means that we go back to exactly what we saw before for quadratics and for spatial branching. So you branch at d transpose x hat. So you impose the branching rule that d transpose x is lesser than or equal to d transpose x star, or d transpose x greater or equal than d transpose x star. And you use exactly the same set of techniques you would use in spatial branching when you used it on single variables. This technique is a generalization of branching on single variables, and there are very smart ways to find the right D in such a way that with this branching rule and the associated linear inequalities, you chop off a lot of the feasible set. Not only a lot of the set that doesn't satisfy the inequalities. Not only this, the application of this sort of technique was not even in branching. So the authors actually proposed to use this, which is a disjunction, to get disjunctive cuts, which we also saw in this course. So you use this disjunction in order to get an extra cut that is going to help you chop off some of the solutions you don't like by not branching, but simply through a valid cut. So we only saw the simple side of this thing, but the complicated one is a smart way to find a D so that this shape is good for disjunctive cut purposes. So you need to find a way, when you need to find this disjunction that when plugged into a framework for generating disjunctive cuts will give you a deep, a strong, a tight disjunctive cut. This is a slightly more intuitive work, and it uses our beloved perspective reformulation. Suppose you have, this time it's a mixed integer quadratically constrained problem. So you still have a quadratic objective function, a bunch of quadratic constraints. This time I'm using two different names for continuous variables and for binary variables. So we have binary variables y that are sort of switch variables for the variables x. In other words, xi is equal to 0 when yi is equal to 0. And it's bounded between negative big M I and positive big M I whenever yi is equal to 1. This is a technique that you all know because of everybody. We actually looked at it in this course, but you probably already knew what the big M constraint is. Okay, so problems with big M constraints are usually nasty, even without quadratic constraints. When a quadratic constraint comes in, it's even trickier because now you would like to use the fact that the x variables are switched off by their corresponding y variables. And this is a technique that is that can help you with that in some cases. So in principle, you could even have a non-convex problem, but for simplicity, we can suppose now that the problem is convex. So at least the constraint we'll take is convex. So the Q, the corresponding Q matrix, is positive semi-definite. What happens in this case? Let's suppose that Q itself is positive semi-definite. And in fact, it's positive definite. So it has a minimum eigenvalue that is strictly greater than 0. If it's just above 0, it's not really worth to apply this technique. But if it's a sizable lambda, then what you can do is the following. So Q in principle can be simply rewritten, again, I'm not really doing anything to the problem, as lambda times the identity matrix plus another matrix R. Again, lambda is the minimum eigenvalue of Q. And if I do this, I get lambda times I plus R, and R is still positive semi-definite, right? So what can I do now is rewrite the constraint. I'm not changing the constraint at all for now, but I can write it simply as lambda times the inner product between x and x, plus a new quadratic form that is with R instead of Q. And then I just add in the linear part that I had before. So that part doesn't change. Okay, here comes the nice part. yi equals 0 implies xi equal to 0. So in principle, I could take that lambda x transpose times x and replace every xi term, because lambda x transpose times x is going to be lambda, the sum over I from 1 to n of xi squared. I mean, this is really obvious. I don't like this xi term squared, so I simply replace it with 2 times zi, where zi is a new variable. So I introduce yet another variable. And then I simply say that, well, 2zi, because this is a convex constraint with a less than or equal to, I don't need to say 2zi equals xi squared. I can simply say 2zi greater or equal than xi squared. This is perfectly fine. This is a quadratic constraint. But now I strengthen it in the same way that we strengthened those quadratic constraints in the models we saw last week even. Because now I can say, well, but xi is actually turned off by the other variable yi. So I could easily strengthen the constraint and say xi squared less or equal than 2zi times yi. So up until the replacement of these xi squared terms with 2zi's, I didn't really do anything to the model. I actually added an extra variable, but the bound I would have gotten would be exactly the same. But now with this strengthening due to perspective reformulation, I get a much stronger constraint. There it is. So I start from a convex quadratic constraint where Q is not only positive semi-definite, but it's positive definite. I decompose it, I get the minimum eigenvalue. This is an operation that is not very expensive, even for large matrices. And I rewrite the quadratic constraint like this. It's still a quadratic convex constraint because R, once again, is positive semi-definite. There's an extra linear term over there, and then there's an extra few constraints, some of which are rotated second-order cones, and some of them are the other big M constraints. Now, I told you what the method is. Now, you prove that the second set is a restriction. So the second inequality is stronger. What do you need to prove? So take not only the inequality, of course, but everything else that follows is stronger than the one on top. Why? We could rewrite the first one and say X transpose X plus X transpose R X plus B transpose X plus F transpose Y less or equal than C. This is the first inequality. The second inequality is only differing in this term, which becomes 2 lambda. Wait a second. This should be a lambda times X transpose X. Sorry. So this is actually the original inequality. I forgot to put a lambda in front of this inner product. 2 lambda sum over I of Zi plus exactly the same stuff. So I don't even really need to compare the rest. I just need to compare these two terms, knowing that xi squared is less than or equal than 2zxyi, 2ziyi, and we could even forget about we can even prove it without the big M constraints. Can you prove that based on this information, this is stronger than that? What do I mean by stronger, by the way? I'm sorry? Yes, this inequality generates a subset of this inequality. Okay, I don't want to deal with subsets. This is a number. What do you want to prove between these two guys? The above is? The above is smaller or bigger? The lower is smaller, always. You sure? If the lower is smaller, then we have a less than or equal to constraint. We are weakening that constraint if we put in a smaller quantity. So if we have a quantity here, and we want to strengthen this inequality, we better take something that still gives me a valid inequality, but it gives a larger number than this. So the proof, we would like to prove, in fact, that 2 lambda sum over I of Zi is greater than or equal to lambda times X transpose X. Or let me write it explicitly, sum over I from 1 to n of xi squared. Can you prove this with the extra inequality underneath? Say it again. Use the second constraint? Yes. How? Do you want to write it? Did you use y for your proof? I'm not sure I understood the proof. That's
this comes like for every I.
Sorry, this is a 2, by the way.
So for every I, we will have xi square that will be less than or equal to 2zi. So if we add these constraints,
Okay, even easier.
This can simply be written as x transpose.
That's correct.
So multiply both sides with n, you get the result.
Exactly. So this inequality is always satisfied. And you can suspect that for larger alphas, obviously, the larger alpha, the larger the difference between these two terms, and the stronger your cut.